Programming.
Thank you, John, and thank you for the organizers for giving me this opportunity to talk, and for also I thank you that you stayed here late in the afternoon. And I'm gonna hopefully finish by 5 so that you can go and have your first beer by 5:30. Okay. So I'll talk about the degree of central curve in quadratic programming, and this is joint work with one of my master's students. Now he's done, and he's a PhD student at Carnegie Mellon OR department, and part of his thesis is sort of part of what I'm going to talk about today. Okay. So what's a quadratic program? Quadratic programming is an optimization problem. Okay, we're trying to minimize a quadratic objective function, okay, given by a n by n symmetric positive definite matrix, and then there's also a linear part too, subject to linear equations, and the variables are non-negative. Okay, again, in this case, the Q is a positive definite matrix. C is some cost vector. A is a D by a matrix of rank D. So keep in mind, D is the number of equations and N is the number of variables. So, in my formulas, the D and N are going to appear. Okay. So as I stated, this is a convex optimization problem, because when I have a positive definite matrix up there, it's got a convex objective function, and the feasible region is also convex. This is sort of all the nice technology we can apply, right, of optimization, the convex optimization. Okay, so how would you solve such a problem? Okay, here's one way of solving, so like a 10,000 feet point of view of interior point methods. You change your problem just slightly. You put in the non-negativity constraints into the objective function. Okay, lambda is a positive parameter there. Right now, as lambda, so you should imagine that you're going to solve this problem. Okay, as lambda starts big, plus infinity is going to go down to 0. Objective function is still convex. Okay, and when lambda is really super big, okay, then we can get the optimal solution for this problem very easily, because the original objective function part sort of disappears. That's not going to affect. And then as lambda goes down to 0, the original objective function is going to take over, right? And we'd like to sort of use that. And how can you sort of turn this into equations, right? Optimization problems is really solving systems of equations, right? I can write down what's called the KKT conditions, the Karish-Kuhn-Tucker conditions, and here they are. The first two are the feasibility conditions on x, ax equal to b, x non-negative, and then comes sort of the gradient of the objective function. Okay, that's this first part there, and then that's equal to a linear combination of the rows of the matrix A. Okay, so y is a vector of variables, y1 through yd, so there are y variables there. So the nice thing is that, so we have a convex problem, so if you solve this problem, there's going to be a unique solution when for each lambda that's positive, okay, and the x component of that solution is going to give you an optimal solution for the above problem there. Okay, so we're going to do that, and so again, for every lambda there is a unique solution. So for every lambda there is some solution here where x star is going to be the optimal solution up there. Okay, and then we can vary the lambda, right, and plot the pair of optimal. Actually, the y is sort of the optimal solution for the dual. Okay, we can plot that, and then we're going to get a curve in r to the n plus 1 plus d. Okay, this is a small example that I'm going to use to illustrate some of my things here. Okay, here is a quadratic optimization problem. Very simple quadratic function there. So the Q matrix is actually a diagonal matrix now. Okay, and the linear part, and then two equations in 4 variables. As you can see, I chose my equation in such a way so that x3 and x4 can be easily expressed in terms of x1 and x2.
Just a stupid question on the last slide to make sure I'm not lost.
Yeah.
So your actual solution is just the first solution where all the x's are positive with the smallest lambda, because you have this curve, and that's the point on the curve you take?
Say again? So when lambda is super big, yeah?
When lambda is 0, you don't have positivity, but eventually it's going to force it to be positive, and you're saying that first point it's forced to be positive is the actual solution to your original question on the previous slide?
No, what I'm saying is I start with lambda being super big, okay? Yes. I solve a sequence of problems, As lambda is approaching 0, okay, I'm going to also approach the optimal solution to the original problem.
Why does that keep the x positive as lambda goes to 0? I don't see that.
Because of the logs.
Oh.
It's a barrier function.
Yeah, okay.
Sorry. Okay, so that's my problem. So again, so after that, I'll come back to my example right away. Let me make a central definition. Okay, central definition of central path. Okay, so if I take this curve that I get for every lambda, right? That every point I get the point on this curve for every lambda. I take that and I project it on the x coordinates. Okay, get a real curve. That's called the central path of quadratic programming. Now, meanwhile, okay, maybe I should have said earlier, in my original optimization problem, the quadratic program, of course, if I didn't have the quadratic part, if q were equal to 0, right, then I will have a linear program. Okay? So what I'm saying here can be all set for the linear programs as well. Okay? So the central path can be defined in a similar way using the same kind of optimization problem. Okay, and we will get a central path for linear programming too. Okay, so what are the equations defining these are the KKT equations defining the central path in my problem. Okay, so you see the diagonal Q matrix here. You see the cost vector C up there. Okay, the lambda over the variables appear there as well. And right here you see the transpose of the A matrix, and then the constraints, the AX equal to B constraint down there too. Okay, so we solve this for every lambda. We get a curve projected on X. That's the central path. Okay, so how will we use this? So here's a cartoon idea. Okay, and when lambda is really big, okay, we can solve the problem very easily, and we get something called analytic center of the feasible region of the polytope. Okay, and then we start from there, and we start making the lambda smaller. As we're doing that, we're going to follow the central path, okay, all the way to the optimal solution. Okay, so that's one way of saying how the interpoint algorithms work. In this cartoon picture, you should not be fooled. Okay, I had again the linear programming in mind. The optimal solution is going to be at the vertex. Of course, it doesn't have to be that way. Okay, for the quadratic programming, and there's a unique optimal solution somewhere, but it doesn't have to be at the corner there. Okay? But that's how the linear programs, the interpoint algorithms work. Okay, okay. So now let me go to the algebra or algebraic geometry. I define the central path by projecting the earlier curve on the x coordinates. Now, but the equations defining it were not polynomial equations. I'm going to make them polynomial equations by clearing the denominators. Okay, so what you see here is the KKT equations, but I'm going to multiply each equation by the corresponding xi because they were in the denominator. I'm going to get this polynomial equations. Okay, so and I'll take the complex solution set of them together with the ax equal to b. That's a curve in c to the n plus 1 plus d. I'll project that on the first n coordinates. I'm going to call this a central curve of quadratic programming. All right. Okay, so this is central curve defined by those equations. I cleared the denominators. So well done. Okay, so one more time. I'll project. So the ideal generated by these equations I'm going to call J, and the vanishing ideal, or the ideal that of polynomials vanishing on the projection, the central curve, I'm going to call I sub C. Okay. Okay, so in our running example, okay, if you do the computations, there was a n was equal to 4, d is equal to 2 equations for 2 equations and variables. The central curve, after you do this projection, okay, will be defined by the linear equations, ax equal to b, and one extra polynomial, okay, of degree 4. Okay, this is that. And you see the real picture of the curve. The wall is the ax equal to b, two-dimensional affine space. The lines you see are the intersection of the coordinate hyperplanes with the affine space. Our feasible region, original feasible region, is this quadrangle, by the way. Okay, that's the one. And you see other feasible regions there if I change the signs of the variables. And the rest, the curvy stuff, is the central curve. Okay? And central curve contains all the central paths of all the feasible regions. Okay? And central paths will follow from the analytic center of that particular region to the optimal solution. Is that clear? Okay, so it's a nice degree 4 curve. Okay.
So if you only cared about one of the regions, could you have a simpler curve? Seems like
So the central curve is the way I defined is I forget about the non-negativity. I went to the complex numbers. I take the whole thing and then project it. So I get the whole. Okay, so I think so. Okay. This is an irreducible curve. Okay, yeah, this is an irreducible curve, right?
So I guess the other boundary chambers, if you change the sign system variables, those would then be feasible regions.
Exactly. Yeah. So there are.
So one of those, there's two components of the curve of that, right? The triangle that's just below the quadrant.
I mean this one here.
No, to lower left. Up.
Lower up.
No, no.
Right. Oh, here you mean?
No, just to the right of that. Just to the right of that. Just to the right.
This
of
one.
that.
Yes.
Okay.
There's two components to that curve in there. Sort of interesting.
Right.
I guess
Maybe it goes for a minima. Yeah. Okay.
Anyways.
that's a plotting mistake.
Maybe so. No, I'm not sure.
That's
Yeah.
actually the coordinate. That's not those lines.
Are the coordinate axes?
Coordinate axis.
Oh, I'm sorry. These are not the parts of the curve.
Yeah.
These are coordinate
I
axes.
understand.
Oh,
I
okay.
understand. That's it's a polynomial decomposition of the plane, and for different choices of, say,
Yes.
changing the sign
That's
of the
right.
variables,
Each one of
those
you-
become a feasible region.
That's right, yeah.
And in that feasible region, that triangular region, there's two components of your central curve.
No, but they're saying that these are
Why
coordinate
did
axes, not parts of these are not parts of the conditions, I think.
I'm not sure why there are two components there, but anyway. Okay.
So there's also this quadratic form has some minimum over all of the plane.
The plane, yeah.
right?
I know what it is. It's in here actually, in the original feasible region.
Okay.
And it's not on the boundary. It's somewhere. It's in the middle here,
Okay.
somewhere there, and the central path follows, from analytic center down there.
Right.
Okay? Yes. It's not everything else. All the optimal solutions for all the feasible regions are on the boundary, except that middle guy. Okay. Okay. So the goal here is I like to compute the equations of the central curve. Okay. And try to compute the degree of this curve. Okay, that's why the degree of the central curve. So why? Okay, so this work of studying the central curve and interior point methods using differential geometric methods were started actually by Dave Bayer and Jeff Lagarius in the late 80s. But then sort of recently, two new things happened. One of them is that my office mate Gregorio Malajovic and Mike Shoup and Didier, how did I say it? Didier, okay. It's in 2005. Looked at the central path and looked at the total curvature, okay, of the central path for linear programs. So why would you want to look at the total curvature of this curve? Well, as I just described to you. Oops, the other way. Okay. Let's go back to the cartoon. Okay, so if I'm going to follow this path, right, I have to make steps, right? I cannot continuously deform, lambda from positive infinity to 0. I have to make steps. So that means I'm going to be approximating this curve by a polygonal path. Okay, the curvier the path, the higher the total curvature, it's going to be more difficult. So the higher the curvature, the total curvature, then there's going to be the interior point algorithm are going to take more time, more iterations to get to the optimal solution. Okay? So that's the rough idea. So they looked at that, and so their idea was that, well, okay, the total curvature is actually can be computed by looking at the arc length of the corresponding Gauss curve. Okay? So you look at the unit tangent vectors to the curve, you plot them on the unit sphere, and you compute the arc length. And that arc length can be bounded, okay, by data coming from the central curve itself, including the degree. Okay? So that was the idea. Okay? And then comes Jesus and Parent and Cynthia, okay, in 2012, actually earlier, that's published in 2012, and they actually gave a bound, okay, for the central curve in terms of d and n. Okay? So they say that the degree of the central curve for linear programming is n minus 1 choose d. N is the number of variables, d is the number of equations. Okay? And this bound is sort of exact when all the data, the A matrix, the B and C and everything is generic, okay, if it's randomly chosen. Okay, so that's the degree of the central curve. In particular, it implies a bound on the total curvature that I'm just putting down there. Okay. All right. So that's a bound on central curvature. Now, one of the motivations of all the study is that there's been a conjecture in the back, and out there. It's called continuous Hirsch conjecture. Okay, that says that for any D, okay, you don't have to fix. Okay, for any D, for linear programming, the total curvature should be a linear function in n. Okay, we're bounded by that. It turns out it's a very new result by Mikhail Yosvik and his co-authors that actually spectacularly false. Okay, it's the total curvature of the linear programming can be exponential. Okay, if you allow D to also vary. Yeah, and it's a very interesting paper. I have to look at it more carefully, but it involves heavy-duty tropical geometry in there. And then finally, one of my motivations here is that quadratic programming. So we deal with linear programs. The ultimate goal is really, look at semi-definite programming. It has its own central curve and whatnot. Okay, and quadratic programming is a one step in between. Okay, although of course the semi-definite programming is a little far away from quadratic programming in a sense. And I know, smart people like Cynthia have thought about it, and it's a hard problem, but that's sort of the goal. Okay. Okay, so I hope the problem is clear. I want to look at the equations of the central curve for quadratic programming, compute the degree, and these are the reasons. Okay. Okay, so this is my embarrassing slide. Okay, Ben already mentioned whether this curve is reducible or not. Okay. To tell the truth, I don't know. Okay, in generality, it should be reducible. But here is one simple observation I'm going to use. This says that if I take the upstairs curve and remove the coordinate hyperplanes and then close back again, nothing changes. Which means that the central curve does not have any components, if there are any, in the coordinate hyperplanes. Okay. Of course, if we're reducible, we're fine. Okay, that is not going to happen. Okay. But the only thing I'm using is this result anyway. Okay, but I agree with Ben that this curve should be reducible in general. Okay, okay. So here's our first observation. Okay, so now we're going to, Bernd and Cynthia and Jesus have a way of computing the degree using some metroid theoretic methods. Okay, n-1 choose D is actually the number of bounded regions inside a real hyperplane arrangement, okay, that comes from A and B and C. Okay? But we're going to sort of now move away from that idea. And here's our first result. Okay? It says that if I wanted to compute the degree of the central curve, right, what I would do, I will intersect it with a random hyperplane and count the number of points. Right? It turns out all I can do is I can take the upstairs curve and intersect it with a hyperplane, okay, only in x's, okay, then the number of solutions in the torus, in the corresponding torus, is going to be equal to the number of solutions downstairs, and that's exactly the degree. Okay?
So why do you only intersect with the x's and not with the generic hyperplane?
Okay, so one more time, if I project it on the x variables, right, then I get the central curve, and I want, to compute this degree, I will intersect it with a hyperplane like this. What I'm saying is that do the same thing upstairs, okay? You will still have the same number of intersection points upstairs. Okay? All right. So another thing I have to tell here, it was actually a crucial point.
So I guess the point, it can't be several to one.
No, it's not. It's not, right? It cannot because of the AIs here, yeah? The A matrix there. All right, so it's 1 to 1. And then one more thing is there that, so I'm assuming here, by the way, everything is generic. But already in my example, I was using a quadratic, a diagonal matrix. It turns out, okay, if you replace everything in here, where everything is generic, but Q is a diagonal matrix with generic diagonal entries, then okay, the number of solutions you will get for the corresponding system is the same as the number of solutions you will get for the general system. Now you might say, what's the big deal? Every symmetric matrix can be turned into a diagonal matrix, but that's not the reason here. Because if you do that in your, let's see, okay, you will screw up your system. Right? Back here, if you do that, one more time, if you make the change of coordinates, okay, these guys in the denominator is going to become some complicated linear forms. Okay? You have to clear those denominators, and the problem is going to get complicated. Okay? So the reason why I can go down to go look the number of solutions doesn't change when I move to the diagonal programs, because I can have a homotopy from this the general case to the diagonal case. Okay, so and nothing happens in the sense that I don't lose solutions when I do the homotopy. So this is very useful, right? If you think about it, if I want to compute the numbers, right, I can only use examples where the matrix is diagonal. Okay, and that makes the computations a lot easier. So when we tried using Grosvenor basis methods, to eliminate and then compute the degree, we were able to compute a very small portion of this table. So here, these are the degrees for generic cases where that d is the number of equations, n is the number of variables. Okay? We're able to compute a very small portion, but for the diagonal case, we can complete a big chunk of the table. Okay, and in fact, we did this earlier. We realized it, and then went back and proved the earlier theorem. Okay. Okay, so these are numbers. Hopefully you think that these numbers are nice. Okay. All right. Very good. Okay, like the first row, fantastic. Okay, exactly. Oh wow, Frank is fast. Okay, so you see that, right? What is it?
5 plus 11 is 6.
Exactly. This is equal to that times that. It's very nice. All right. So okay. So how we're going to do this? I'm going to do is I'm supposed to count the solutions in the torus. Okay. I'm going to do that for you first for the linear program. Right? So this is the linear program version. So I'm going to compute for you the degree of the centrifugal for linear program. Okay? I need to count the solutions here. These are d plus 1 equations in n variables. Right? I write the solutions. So this is a n minus d minus 1 dimensional affine space. Right? Every solution looks like that. So V1 through Vn minus d. V1 is a vector in the kernel of the matrix. Right? So I introduce new variables, T1 through Tn minus d minus 1. Okay? I take that, okay? I plug it in upstairs where I have the x's. Okay? I expand it out. So I have n equations now in n variables. And the support of those variables are exactly these guys. Okay? So what are this? The supports of the equations. Okay, note that. So the lambda I can ignore. Okay, 1, T1 to Tn minus d minus 1. That thing multiplied with the y1. That thing multiplied with y2, etc. Okay, that's the support. Okay, so what is that? Okay, that's also known as the n minus d minus 1 simplex cross d-dimensional simplex. Okay? And every equation has that support. So in order to compute the mixed volume, I'm going to compute the normalized volume, i.e. the volume of this guy. Okay? The volume of this guy, also known as the Cayley polytope of what is it? D copies of n minus d minus n 1 dimensional simplices. I'm sorry, d plus 1 copies of them. Okay? And the volume is computed like that. It's actually n minus 1 choose d. Okay? And I'm going to write it in this form. Okay? So you can get this form as if you look at the staircase triangulation of the polytope. Okay? So this is not very complicated. So what I'm trying to say here, let's say if n was 7 and d is equal to say 3, okay, then 6 choose 3, right, can be written as what is it? 5 choose 2 plus 4 choose 2 plus 3 choose 2 plus 2 choose 2. Okay. Right. But so n minus 1 choose d in this view has this nice decomposition into sums. Okay. So I'm going to do exactly the same thing for the quadratic programming. Okay. So same thing, just the quadratic part has included here now. Okay. I'll do the same substitution. Okay. I do that, and this time I'll have monomials in the support of the following kind. Okay, so what do I have now here? I have first 2 times the simplex, n minus d minus 1 simplex, and then d copies of the standard unit simplex shifted in the directions. This is the Cayley polytope of 2 times the unit simplex, and then d times the unit simplex. Okay? D copies of the unit simplex. Okay? So we can compute the volume of that polytope, okay, by using the staircase triangulation too. Okay? But this time you get the exact same thing with the volume factor. Okay? Each one of those guys is going to have 2 to the k. Right? So that's the i.e. I'm going to put here. Okay, the volume is going to be, so it's going to be 2 to the 0 plus 2 to the 1 to the square to the cube. Okay, so that gives us the degree of the central curve for the quadratic program. It's very, very close to linear program in form, and then we get that.
So in this case, then the BKK bound is exact.
Exact. Yep. For the generic data, it's exact. Do I have 2 minutes? 2 minutes I have. So the triangulation. So let me just point out something here. In the case when, again, Q is a diagonal matrix, okay, we also have the equations for the central curve. Okay, we use a nice idea to eliminate the variables, and if I have time, I can explain it to you. Okay, but I don't have the time. Okay, but the point here is that with respect to a degree reverse X order, okay, exponents and xn, let's say for d is equal to 2, a is equal to 5, I get the following Grobner basis, plus of course ax equal to b, the equations, right? The initial ideal, okay, is generated by those 4 monomials. Here is the decomposition, okay, and if you add up the degrees, it's going to be equal to 11. It should be the case. Okay? If you erase the 2's, okay, you're going to get the broken circuit complex, okay, of the uniform matroid of rank 3 on 5 elements. Okay, so using actually the degree bound, okay, we were able to prove that these are the equations that define the curve as well. Okay, I'll stop with that. Thank you very much.
So any quick questions? Yes, Cynthia.
So this thing that these equations define doesn't depend on B?
No, it depends. So you see the numbers here?
Yeah.
The numbers here. So what doesn't depend is the terms do not depend. So I chose a specific problem, but I generated my B's and C's randomly and did my prediction.
You had these equations
Earlier.
And you could eliminate this long equation with lambdas and C's and Y's and all of this stuff.
Yeah.
The long ones didn't have any B's in them.
Right. Oh, I see. That is correct. Yes.
I was wondering if there was.
No,
like
you're right.
geometric
Exactly.
description.
This doesn't have any data that comes from B. I agree with you. You're right. I'm
I was wondering if
sorry.
you had like a sort of geometric description of what this large variety is.
Yeah, this is now the central sheet, right, for the quadratic programming.
So the part from B is just slice it. You slice this.
Yeah, with ax equal to b. Then I slice
So
it.
that slices, but this.
That's
is
right. But this, you're right. This doesn't
So is there
doesn't
an
contain
analog
b.
to the central sheet?
I mean, it is the central sheet. You know, I'm calling the central sheet, but I don't have anything like that comes from like Spires and Broadfoot's type of result. I don't have that. Yeah. But this monomial ideal, hence this initial ideal for this guy. In general, you know, this is a Cohen-Macaulay initial ideal, right? So we can compute the H vectors, and in fact, so that actually we can get a good bound on the central curve.
Any other questions? Yes, Matt.
Yeah, so you mentioned that this is for all generic data.
Yeah.
So then what about if you say for that Q term, that Q matrix, what if this guy was sort of rank deficient? I mean, so it's no longer generic anymore. How does this affect things?
It should go down, but I don't know how in a controlled way it's going to go down.
Do you think the curve would still be irreducible then, or do you think it might split up into different irreducible components, or?
I don't know.
All right, let's thank Serkan.